So hello guys, we are going to cover E2 quantum physics in this video. So this is an actual topic, and in this topic we are going to cover some effects that led to discovery of quantum physics. And we are going to start with the photon. Photon is a massless, chargeless particle, but it do have some energy and momentum associated with it. The energy of a single photon is, we already learned this, we can calculate using hc by lambda or hf. And the momentum of a photon is calculated by h by lambda or E by c. H by lambda is Planck's constant upon the wavelength of the photon or electromagnetic wave, or it can be energy upon speed of light. Okay. Now, if we have a source of power P, power is usually given as energy over time. Now, if there are n number of photons which are released per second, then the time will be 1, and each photon has an energy of hf or hc by lambda. So it will be n times hc by lambda. That's the power. Okay. We don't have any time term because n, capital N, is number of photon released per second. So power can be calculated using this. Similarly, intensity is power over area. So whatever power equation we just have to divide it by the area. Okay. Now let's say a photon collides with a reflector. A reflector is a device which, without absorbing any energy, reflects all the energy of the photon incident on it. So it is a kind of an elastic collision. So if it is elastic collision, then the change in momentum, if we see, it is 2p because the direction of the momentum is changing. And the force is change in momentum per unit time. And since there are n photon are released per second or hitting on the surface per second, it will be per second. So time would be 1, and this will be 2pn or 2mh by pi. So this is our equation for the force exerted by the n photon hitting on the surface. If we want to calculate pressure, again pressure is force upon area, and we get similar kind of equation. Now those are the things that we can work out with the photons and different scenarios. We just have to remember what is the energy and the momentum of the photon represents, and how we can calculate power, intensity, force, pressure, and other quantities. Now we will talk about more important experiment that gave us the evidence for particle nature of light or electromagnetic wave. Okay, so in this, it is a phenomena in which a light is emitted from an electron is emitted. Okay, light is incident on the metal surface. So we bombard metal surface with photons or light, electromagnetic wave, which leads to ejection of electrons from the metal surface. Okay, so this is a photoelectric effect. Now we will learn specifically the experimental setup behind this. According to an experimental setup, what we have is a vacuum tube, and inside a vacuum tube we have 2 electrodes. One is negative, other is positive. Now those electrodes are connected to an extremely high variable voltage, while there is a gap for the light to fall on the metal surface. And there is also a galvanometer. So this is the setup for the experiment. So what we do is, like, as the light falls on the metal surface, electrons are ejected and few of them gets repelled by negatively charged plate. So there is a repulsion that is happening, you can see. So those repulsion will make sure that low energy electrons are rejected, while some high energetic electrons reaches to the negatively charged plate and causes a minor current, which is detected by galvanometer. So galvanometer or ammeter will detect the minute current that is caused by the electrons reaching from the metal surface to the anode. Now, as we keep on making the voltage high enough that the anode plate can now repel even high energetic electrons. So it can repel high energetic electrons, but if we keep on increasing the potential difference, at a certain point, when a potential difference attains a value at which no electron reaches the anode, that is, there is no current, the current that is detected by galvanometer drops to 0. That potential difference is called as stopping voltage. So this is very important. So let me repeat what is stopping voltage. It is basically a voltage at which the negative plate can repel even the highest energetic electron possible, and which leads to no current, 0 current. So that is the stopping voltage. So conservation of energy suggests that the energy due to the stopping voltage, that is the potential difference, okay, is equal to max kinetic energy of the electron. So charge times electrons into stopping voltage is max kinetic energy of the electron. And the graph of E versus V, photocurrent of the current caused by the electrons, is equivalent to this. Okay, so we will get a graph like this. Now for the graph which is on the positive side of this y-axis, this graph is only achieved by reversing the terminals of the battery in the setup above. So that will give us. Now there is also a saturation. Okay, so what happens? We reverse the power supply, increase the voltage due to the reverse polarity. Now the electrons are attracted to the opposite, causing the current in the circuit. The current eventually reaches the maximum saturation point, as there is a limit on how many electrons that can be ejected from the given metal. Okay, so this is where a saturation for the current is reached. Now, what are the observations of this experiment? There are four major observations that we probably need to remember. There are a lot of questions asked on this. The first is the stopping voltage for the given metal does not depend on the intensity of the incident light, while the stopping voltage depends on frequency of the incident light. So this was very surprising observation. There is a minimum frequency for the given metal below which electrons are not ejected. So we can't have any frequency or wavelength. It has to be specifically above the critical value. Okay, so this frequency is also called as critical frequency, the minimum frequency required for electrons to eject. And then the fourth point was there is no delays between hitting the light on the surface and the ejection of the electron. Okay, now those four observations were very important, and this four observations was very surprising because the wave model couldn't explain this. Now, why the wave model couldn't explain this? So, according to wave model, the energy of the wave depends on the amplitude of the wave, and so does the intensity of the wave. So, higher intensity, higher amplitude, all those increases the energy of the wave. Now, if you give enough energy, electrons must be ejected. But what we saw is that with increasing the intensity, there was no increase in the number of electrons ejected. Okay, so the energy for the electromagnetic wave or the light does not depend on amplitude or intensity. Okay, that was the first thing. Second, if the wave was carrying an energy to the metal surface so that the electron is ejected, then there will be some delay, because you can't just transfer energy instantaneously when a wave is passing on energy to a given particle. It will take some time. Okay, and as the real thing observed is that there is no delay. So wave model was not able to explain this, and here comes Einstein's model. Okay, now according to Einstein's model, he suggested the light as a quanta of energy which is called as photon, and the energy of the photon is given by this equation which we already learned. So he says that every metal has something that we call as work function. Now, work function is minimum energy required to eject the electron from the metal surface, and it is unique to every given metal. Okay, so work function, what happens? A photon, according to Einstein's explanation, a photon incoming. Okay, then that photon transfers some energy to the electron. Okay, electron spends some energy to overcome the work function, and once it overcomes the work function, that becomes the kinetic energy of the electron. Okay, so for the work function, it is depending on critical frequency, the frequency below which the electrons are not ejected, and then lambda c is the critical wavelength, the wavelength above which the no current or no electrons are ejected. Okay. Now, from the Einstein explanation, we got an equation that the max kinetic energy of the electron depends on the energy of the photon minus the energy, the work function, that is the energy required to overcome the metal surface. So we get this equation, Ek is equal to Hc minus phi. Now, if I compare this with y is equal to mx plus c, you will find that y should be plotted on y-axis. This Ek should be plotted on y-axis, and this frequency must be plotted on x-axis. So they got a curve like this, okay, which is very much correct because the slope is constant. That is h, that is Planck's constant. The slope is Planck's constant, and critical frequency is where this x-intercept is, and the y-intercept is the work function. So this graph is pretty important. Similarly, we can substitute the kinetic energy as EBS. Okay, that is stopping voltage. So if we rearrange the term, we will get stopping voltage is equal to H by EF minus phi upon E. So basically, stopping voltage is nothing but this energy of a photon. HF is nothing but energy of a photon divided by energy electron charge minus work function upon electron charge. So similarly, comparing with y is equal to mx plus c, if we have Vx and Vf graph, then we will say that the gradient is positive again with the work function upon E as a y-intercept, and the critical frequency also can be shown in the same graph. Now this provides the nature that the light has particle nature, and due to experiments like Young double slit experiment, diffraction, all those phenomena says that the light is a wave. So we later on agree to what we say as dual nature of light. Okay. Now there is somebody called de Broglie. Okay, de Broglie came with an idea that he suggested that every particle in nature has a wave associated with it, such that the wavelength is given by h by p. Okay, so he stated that every particle is in nature has to be having some kind of a wave associated with it. Okay, so this is the de Broglie hypothesis, and this is the formula for de Broglie hypothesis. Now, why does every particle carries a wave? Why does not we observe them? Because the momentum, see, h is the Planck's constant, h is 10 raised to minus 34. If the momentum is not of that comparable sizes, if the mass is not comparable sizes, then de Broglie wavelength won't be observed. So, to do that, we need to have extremely high energetic particles, okay, so that they will have that momentum, and that will come with a wave associated with it. We can observe the wave nature. Now, to test this, there was an experiment called Diffraction experiment, where an electron diffraction was observed. So basically, what they did is like they accelerated electron between the metal plates with a potential difference V. The potential difference is work done upon charge, so change in energy is work done upon charge. So energy is basically E2. So momentum is given by, it is actually p square by 2f, but we can rearrange this to get root of 2fe, and p is equal to root of 2mev, because capital E, that is a change in energy for the electron, is equal to the electron and volts. Now, thus the wave associated with the electron is given by lambda by, okay, lambda is equal to h by. So all we need is divide, substitute what is p, and we got this relationship. Okay. Now the Diffraction experiment setup was like this. They have electron which can be accelerated and has a low energy. Low energy because we don't want them to pass through the metal, but rather react metal or reflect side heat. So the reflected beam is observed in the detector. What we saw is that we saw an interference pattern. Why there was an interference pattern? Because there was, when you say there are layers which are parallel. So I saw that there are two parallel lines. Okay. And that is the incident and reflected ray. Now, when we figure out the part difference is 2d sine theta. Okay, so 2d sine theta is probably somewhere here. Okay, and condition for interference is 2d sine theta is equal to n pi. So these are the small things that we can remember. Okay, so thus we can calculate. So if we know what is the theta at which the detection is maximum, then we can find out the wavelength. Now, lambda represents wavelength of the wave associated with the electron when calculated through Diffraction experiment. And this, with this experiment, whatever the value of lambda will be calculated is the same value that we got from the de Broglie's hypothesis. Okay. So this is very similar. Now, neutron diffraction. Now, I won't think that this formula is there in your syllabus, but I will feel that neutron beam is bombarded as the atom and diffraction pattern is seen. If there is a pattern like this given intensity of 6 theta graph, then the minima here on the graph, the first minima, is position of the diffraction minimum. Okay, and diffraction minima is given by theta is equal to lambda by b. So that is very similar to what formula I have wrote here, but don't remember this formula is not there in syllabus anymore. Okay. Now, the one last thing about this chapter is Compton scattering. In Compton scattering, a photon is incident on an electron before collision, and after collision, the photon is deflected and loses some energy to the electron. Okay, the angle between the direction of the photon and the collision before and after collision. Okay, so those are the two important things. Now we will get the equation of the Compton scattering, which is given like this. Okay, now what is theta here? Theta here is the angle between the initial direction of the photon and the final direction of the photon. H is Planck constant, and V is mass of an electron. M is the mass of the electron, and lambda dash minus lambda is the change in wavelength of the photon. So whatever the wavelength before and after collision that is happening, that wavelength change is happening. Now we will try to solve few questions. Okay. In an experiment to investigate a photoelectric effect, a beam of a monochromatic light is incident on a metal surface. When a frequency of the light is less than certain threshold, if not, no electrons are ejected. Outline how this observation supports the photon model of the light. Okay. Now here what we can say is that there are two things we have to say. First thing, for photon model of light, we need to understand is that the photon model suggests that there is certain threshold frequency for incident photon because there is a work function for every metal. Okay, so this work function has to be overcome, which has to be overcome by the photon. Okay, and energy of the photon is directly proportional to frequency. Directly proportional to frequency. Okay, not proportional to intensity. According to wave, the wave model fails as according to wave model, the energy of the wave is not dependent okay, on frequency. Similarly, if we get a graph like this, we will see that yi0 for large V, because the V is large enough to deflect even a strongest or highest kinetic energy electron. Deflect large enough to deflect the highest energetic electron. Okay. Now, approaches a constant value after P, as I suggested, that will be a saturation, because there is a limit on how many electrons that can be ejected from a metal surface, and after a certain point, there is an equilibrium attended, and the electrons that are incoming are the only electrons which are given through the conductors. Okay. Calculate the EV. Now, EV can be calculated, energy of the photon can be calculated for the wavelength. So this is very easy. So we can use H lambda. And in EV, we want that we would take 1.24 into 10 to minus 6 and upon 430 nanometers. So that is 9. What is the work function of the metal surface? The work function of the metal surface can be determined because what they have given, you see this. When we get this value, we will get certain value in electron volts. We will get certain value in electron volts. But here they have given you the stopping voltage, that is 0.9 V. So if the stopping voltage is 0.9 V, then the kinetic energy, max kinetic energy, will be EVS. But E we multiply only when it is in joules. So what we do is basically it is 0.9 EV. Okay. So we don't have to convert the volts into joules again and joules to electron volts again. Okay. So this is directly can be done. It is 0.9 EV. Similarly, if we use this formula, the max kinetic energy is equal to HF minus pi. Okay. So this is 0.9 is equal to HF. So HF, we already calculated, this value will come here. This is always in the electron volt, so it is easier for us to subtract. And then we have to find a work function. A work function can be found out by this equation, and we will get our answer like this. Now, in this demonstration, what is happening? There are three radiation sources given. In metal P, for this wavelength 3 into 10 raised to minus 7, the metal P electrons are emitted for both the metal P and metal K. For 6, only for metal P is ejected, not for metal K, and for 8, both have not. In this case, what is the cause of electron emission for radiation? You can say that for radiation, because the wavelength given is greater than the work function or the energy required for the work for the electron to jump out of the metal surface. Okay, that is greater. So what we can say is that the energy of photon of wavelength 3 into 10 raised to minus 7 is greater than energy of the metal P, minimum energy of the metal P, or we can say that then the work function of metal P and Q. Okay. So why the electrons are never emitted from the C? Because obviously the wavelength given is higher than the wavelength, okay, than the critical wavelength. So critical wavelength is a wavelength above which the energy is such that the work function is not satisfied, no electrons are ejected. So these are the conditions that you can answer. Explain why there is no effect of doubling the intensity. Because intensity, when we increase the intensity only increases the number of electrons or photons ejected per second. Okay, and it does not increase the energy of a photon. Doesn't increase energy of the photon. Each individual photon, it doesn't increase. If the photon energy is given, what is the work function? Again, we can use the same kind of equation. Okay, but here the direct energy of the photon is given. This is the direct energy of the photon, 1.1 into 10 to minus 18, and then the maximum kinetic energy is also given in joules. Both energies in joules we will get pi in terms of joules, and then we convert that, we will get in electron. Okay, so these are all the questions we have. Now, last two MCQs we will do quickly. Now, in this question, what is happening? A light falls on a metallic surface whose threshold frequency is f0. Okay, now the number of photons incident per second is constant. Now, which graph correctly shows how the current I emit from the surface depends on the frequency. Okay, so below frequency there will be no current, and after certain frequency, if we are keep on increasing, we will get a constant current. Because see, the light number of photons incident means intensity is same, so intensity is not changing, then the amount of current will be also be constant, not increasing. Okay, the light frequency of F on a metal surface has a work function W. The photoelectric effect has a max kinetic energy E max. The frequency is now doubled. Now, what is true about the max kinetic energy and the work function in the second scenario? So earlier it was EK, the max kinetic energy, HF is minus W. It was okay. Now what has changed? It has changed from HF to F. There will be new W dash and then new kinetic energy. Okay. Now, obviously, when we talk about 2 times Emax, basically it is equal to 2 times HF also and 2 times the minus 2 also. So you can see that the max kinetic energy here, E dash, is rather greater than the 2 EK. Because in 2 EK, we are subtracting 2 W from the 2 HF. Here we are only subtracting only 1 W from 2 HF. So it is greater than that, and omega, the work function, is not changed, because for the same metallic function, the work function won't change. So the correct answer is C. Okay, work function does not change. Similarly, here what is in the graph given? A metal surface is replaced by the one which is less energy to remove the electron. Correct? Now, the EK versus F graph, the gradient represents H, that is Planck's constant. If you look at the equation, H is the Planck's constant, is the slope. So here B and C are incorrect option because slope won't change, and this represents F naught. So when they say less energy to remove, then we have to have less smaller frequency or critical frequency. The correct option here is A. So like these questions are expected in this particular chapter. Okay. Now, apart from this, we can practice textbook question, but this is all it is there in E2. Okay. So thank you so much, guys.